In this module, we will review the solutions for the response of single-degree of freedom oscillators. Full analysis of single-degree of freedom systems can be found in a number of textbooks on the topic. In this review, we will concentrate on developing a basic understanding of the solution methodologies and to comparing the key aspects of different types of oscillating systems. Specifically, we will examine undamped oscillators undergoing free and forced vibration and oscillators with viscous damping also undergoing free and forced vibration. The basic properties of solving for the response of the system will be discussed, and key attributes of the solutions will be compared. A single degree of freedom oscillator is typically represented as a lumped mass connected to a fixed ground through a spring or dashpot. In our analysis, we will assume that the spring is a linear spring with stiffness K and that the dashpot is a viscous damper whose force is equal to the product of the damping coefficient C and the velocity of the mass. The displacement of the mass is a time-dependent function x of t, and we will assume in general that the mass has an applied force f of t acting on it. The rollers on the mass are assumed to be frictionless. The equation for the single degree of freedom oscillator is obtained by applying Newton's second law. The sum of the forces is equal to the product of the mass and the acceleration. The three forces that are acting upon the mass are the applied force f of t, the spring force, which is a restoring force k times x of t, and the force from the dashpot, which is c times the velocity dx dt. Summing forces and moving the terms dependent on x of t to the left-hand side of the equation yields a standard equation of motion for a single degree of freedom oscillator. Note that throughout our analysis, we will denote the derivative of x of t with the standard symbol in dynamics x dot of t. So in summary, the equation of motion for a single degree of freedom oscillator is mx double dot plus cx dot plus kx equals f of t, where m is the mass, c is the damping coefficient, k is the stiffness of the spring, and f of t is the applied force. Throughout our analysis, we have assumed that the mass, damping, and stiffness coefficients do not change with time. For this reason, the equation of motion that we will study is a linear, time-invariant, ordinary differential equation in the displacement variable x of t. This review will focus on 4 different types of vibration problems. When the damping in the oscillator is assumed to be 0, the system is said to be undamped. In this case, we can study the problem of free vibration, which occurs when there is no applied force, and forced vibration when the applied force is non-zero. Free and forced vibration can also be studied for the case of an oscillator that includes viscous damping. The equations of motion for each of these problems is shown on the chart.